Hey, welcome to The Explainer. Today, we're going to break down a fundamental rule of the universe, one that connects some very different everyday objects in a surprisingly simple way.
I mean, they might seem completely different, right? But believe it or not, they are all governed by the same elegant piece of physics, the ideal gas law. Okay, let's dive into how it all works.
So, first things first, to use this powerful recipe, we have to make one tiny, simplifying assumption, that we're dealing with an ideal gas. Just think of it as a perfect, simplified version of a real gas. This is what makes the math so clean and predictable.
So, when does a real gas start acting like this ideal version? Well, it happens when the pressure is low and the temperature is high. Think about it. If the particles are really spread out and moving super fast, they barely have a chance to interact with each other. So for our purposes, we can pretty much ignore those tiny forces between them.
The ideal gas law is really all about the relationship between four key properties of a gas. So to really get the full recipe, we've got to get to know the ingredients first.
First up is pressure. I want you to imagine a wild storm of microscopic particles all playing bumper cars with the walls of their container. The more collisions there are, or the harder those collisions are, the higher the pressure. We usually measure this in atmospheres, and 1 atmosphere is basically the pressure we're all feeling right now.
Next, we have volume. This one's pretty straightforward. It's just the amount of space the gas is taking up. And here's a cool thing about gases. They're ambitious. They will always expand to fill every single nook and cranny of whatever container they're in.
Then we've got the amount of gas, which chemists measure in a unit called moles. Now, don't let the word throw you off. A mole is just a handy way of counting a huge number of particles. So more moles simply means you have more gas stuffed into your container.
And finally, temperature. For a gas, temperature is basically a measure of speed, how fast its particles are zipping around. Hotter means faster. But here's the part that is absolutely crucial. For the ideal gas law to work, we can't use Celsius or Fahrenheit. We have to use the Kelvin scale, where 0 isn't just chilly, it's absolute 0, the point where all particle motion completely stops.
Okay, so we've got our 4 ingredients: pressure, volume, amount, and temperature. Now, what's so incredible is how they're all connected by one simple, really powerful formula.
And there it is, PV equals nRT. It's so elegant, isn't it? It tells us that pressure times volume on one side is always proportional to the number of moles and the temperature on the other. If you squeeze the volume down, the pressure has to go up. If you heat the gas, either the pressure or the volume has to increase. They're all locked together in this perfect mathematical dance.
And what about that R in the middle? That's the ideal gas constant. You can think of it as the magic conversion factor. It's this universal number that makes sure all our different units, liters, atmospheres, moles, and Kelvin, all play nicely together in the equation.
All right, this is all cool in theory, but can we actually use this formula to predict something in the real world? Oh, absolutely. Let's solve the mystery of our party balloon.
So here's our challenge. We're filling a balloon with 4 moles of helium. We know the room's pressure is pretty standard, and we know the temperature. The only thing we don't know is, how big is this balloon going to get? Let's use our formula to find out.
Okay, let's lay out what we know. The pressure, P, is 1 atmosphere. The amount of gas, N, is 4 moles. The temperature, T, is 22 degrees Celsius. Oh, and remember, we have to convert that to Kelvin, so that's 295.15 K. The only unknown left is the volume, V.
So we just take our master formula, PV equals nRT, and with a little bit of simple algebra, we rearrange it to solve for the one we want, volume. So V equals nRT divided by P. Now for the fun part. We plug in all our numbers, the moles, that gas constant, the temperature in Kelvin, and the pressure, and we run the calculation. And the result? 96.9 liters. Whoa, that is a massive balloon! And we figured out its exact size without ever using a measuring tape. That right there is the predictive power of the ideal gas law. But the power of this equation goes even deeper. You see, it's not just one law. It's kind of like a whole collection of laws all rolled into one. It's like the Swiss Army knife for understanding gases. You might remember some of those other gas laws from science class, like Boyle's law for pressure and volume, or Charles's law for volume and temperature. Well, the amazing thing is, you don't need to memorize them separately. They are all right there, hiding inside PV equals nRT. It just shows you how fundamental this single equation really is.
So why does any of this matter outside of a chemistry class? Well, because this simple formula isn't just a concept. It's a critical tool that shapes our world and even helps keep us safe.
Yeah, this isn't just for balloons. The ideal gas law is absolutely critical for engineers and scientists. It's used to calculate the precise air mixture in a scuba tank, to design the pressurized cabins that keep us safe in airplanes, and to run chemical reactions safely and efficiently in labs.
So, from a simple party balloon to the air in a scuba tank, all the way to the atmosphere that surrounds our planet, the behavior of gases can seem pretty complex. But it's a powerful reminder that sometimes the biggest, most chaotic systems in the universe can be understood with a single elegant idea. Thanks for watching.